Welcome back. So, before our talk, before this talk, I'd like to make an announcement. So, as you probably know, our second speaker missed his speak. So, and his talk will be rescheduled to this afternoon. Today, this afternoon, 1:30 p.m. at the same building here, A14, but different room at 101, just downstairs at 101. Yeah, I'll just repeat again. So our second talk of this morning will be rescheduled to 1:30. Yeah, thank you. Okay, so yeah, from 1:30 p.m. at A14 101, room 101. Okay, yeah, thank you. Okay, now let's uh, okay, now let's begin our last talk of this morning. So our speaker is Raphaël Rouquier uh, from UCLA, and his topic is higher representation theory and low-dimensional topology. So let's welcome our speaker.
Thank you. And thank you for the invitation here. It's a quite extraordinary place and setting. So I'll be talking about some algebra and some connections with topology. So it's a talk that will be dimension 2 and 3. And one of the point is about representation theory, where vector spaces are replaced by categories. And an example that will show up later, just to give you an idea, is a monoidal category that has just 3 objects, 0, 1, and E, where you tensor E by itself, let's say E tensor E is 0. And there are only 0 maps and identity maps, so it's very, very, very small monoidal category. And the claim is that somehow with this category, you can probe at least 3-dimensional topology in a very meaningful manner. So I'll try to say something about that. Okay, so yeah. So representation theory is concerned with vector spaces and prescribed symmetry. So you prescribe a group, you prescribe a Lie algebra, an algebra, monoid, something, and you study systematically representations. And the point is that some algebras, like Heisenberg algebras, have a few irreducible representations. And if you have a vector space with such an algebra symmetries that constrains a lot your vector space, so that's something, for example, that Polonsky and Nakajima used to get better understanding and a new way to describe the homology of inverse schemes of points on the plane or on other surfaces. So using just knowing that a vector space is a representation of some algebra can tell you if you understand that vector space. Right, so that's not something that goes maybe that far, but you can instead of actions on vector spaces, you can look at actions on categories. So there are all sorts of categories of interest, sheets of categories of representations, etc. So some of those categories might have some interesting symmetries. And so higher representation theory, two representation theory is precisely some of the systematic study of actions, possible actions of a given monoidal category. So instead of starting with a monoid or group, you start with some monoidal category, and you study all the possible actions. And So with Joe Schwank, we started that to a very concrete conjecture of Boe about representations of symmetric groups. And it was very concrete. There was a specific functor that had to be proven to be invertible, and it was fairly complicated. People couldn't do that. And eventually we realized that there were some symmetries involved, symmetries of the category, and that instead of having to prove that one specific category had a certain property with respect to those symmetries, we could prove that for all two representations. So think of, in this setting, we wanted to prove that some analog of simple reflection in the Lie group induced some invertible automorphism, some invertible transformation. And proving it on this big representation was daunting, but somehow we could reduce that to the case of a simple representation of the categorical analog, and there it was something we could do. So this idea of higher representation theory came out of trying to solve a specific question. And so that was purely algebraic. There are cases where you find symmetries, categories of geometric origin. So like coherent sheets on Nakajima covariaties, or you can do some sort of D-module or localized D-module or localized perversive version. And this will have a category as symmetries in a sense, I'll say a bit more later, having to do with the Lie algebra, the affine Lie algebra SLD hat. And you can also find symmetries like that on certain categories of representations, Heegaard algebras of symmetric groups at this root of unity. And these are both somehow simple representations, simple higher representations of that SLD hat. So the geometric side and the algebra side both give you a realization of a categorical version of basic representation, the simple representation of SLD hat, and proving that the categories are equivalent. Once you've endowed them with those symmetries, it becomes very easy. You just say, oh, these are both simple, and well, just check the highest weight, and it's equivalent. That's a new way, for example, to recover a result of Ariki in this case. Right. So so to give some so far. The definition of the monoidal category that you would associate to it's a bit like quantum groups where you do things by generators and relations. It's a bit worse, so it's not so satisfactory. I mean, there's no good conceptual way to define things so far. So you can do that completely in a not too long manner for SL2. So representation of SL2, say finite dimensional one, will break into weight spaces. So when we look at two representations, you might want to look at those that have a similar property with weight space decomposition. So we fix a category, an additive category, abelian, that splits into its weight categories, direct sum of weight categories. And then instead of having in SL2, your two matrices E and F act as linear transformations between weight spaces. Now we have functors going from one category to the other. So that would be what people have in mind typically when they think of categorifying an action. They have a category. On the K0 of the category, they have an action of some endomorphisms, and they want to leave these endomorphisms to functors acting on the category. So on the K0, you have endomorphisms. They are the classes of some endofunctors. So in this setting, there's more going on. In addition to these functors E and F, there are certain maps. So you have two kinds of maps, or more. One is an endomorphism of this functor E, and T an endomorphism of E composed with itself. And so the T itself, T is an endomorphism of E transferred with E. So if you take E, if you apply it three times, you have something a bit like a braiding. Okay, you can apply T and then the identity of E, etc. So you require that there's a braid relation. And next, you require that T squares to 0, so it's not quite braiding, and some sort of a Heegaard, affine Heegaard, or degenerate affine Heegaard relation. T doesn't quite swap on E square. You can apply the X on the first or second E, and they are almost swapped by T. And one more thing is that F is required to be right adjoint to E. So that means this category V is a bit like a unitary representation. I mean, we have, we're not looking at arbitrary analogs of representations of SF2 there. Right, so that doesn't tell us everything. What we're missing the important part, which is that the defining relations of SL2 should be satisfied. So if you do the commutator between E and F, you should get H, which acts on the lambda weight space by lambda. So you can express that categorically as follows. So on the weight space on V lambda, if you look at the action of F and then E, or E and then F, we're going to get an isomorphism. So when lambda is positive, there's just a green part, no blue part. We're saying that EF is isomorphic to FE plus a multiple of the identity. So that, when you pass to the quadratic group, is going to tell you that EF minus FE is lambda times the identity in V lambda, which is what you want. And so the crucial part there is that we are not merely asking that the left-hand side is isomorphic to the right-hand side. We're saying there is a certain map, and we're saying this map should be an isomorphism. And that map has two different components. One involves this green arrow. Well, there is a map from composition of E and F to the identity that's coming from the fact that F is right adjoint to E. Now there are many copies of the identity functor there, and we have many maps. So what we can do is first apply a power of this endomorphism X on E. It's called the power of X times the identity. And then we apply the adjunction, the unit of the co-unit of the adjunction. There's something similar for the blue arrow, where we use the co-unit of the adjunction. And then there's this arrow going from EF, E composed with F, to F composed with E. But the data of an arrow from E composed with F to F composed with E, given that F is adjoint to E, is actually the equivalent to the data of a map from E square to E square. That's this map T. So the map T, to be given a map T on the morphism of E square, given this adjunction, is the same as the data of a map from EF to FE. And that's what's here. So these strange maps X and T, when you look at that isomorphism, the data of T is the same as the data of the map there, and the X is already encoded somehow in this green art. Okay, so that's something you can see in the geometry of somehow of Grassmannians versus X is T, etc. So, no, that's one of the mysteries. Yeah, I don't know why. Yeah, I mean, geometrically, it's something you see, so that's why I put it there. But yeah, I don't know. No, I mean, symmetry is a hyperrelation. Right. So now you can study systematically categories. Like those with this. So this is something we call true representation of SL2. I mean, there is a monoidal category, and saying that you have this structure is saying that there's this monoidal category X and V. So there's a notion of category B being simple as a two representation. And for every highest weight, there is a unique, more simple representation too. And there is, if you put some finiteness conditions on your category V, let's say V is abelian and some finiteness condition, then it is, there's Jordan-Euler filtration is going to be built as an extension of those categories. And there can be multiplicity categories, which are going to involve base change as well. And then when you have such a representation of SL2, you're going to get an adjoint action of your Lie group SL2, and I mean, if it is representation of the representational category, and there is in particular the action of the Val group, or action to a central extension of your Val group. There's this element S. In the case of SL2, you have this element, and you can provide a categorical counterpart of that element that involves a certain complex. You have to think that this element small s can be written as a triple exponential E, exponential minus f, exponential E, and exponential E is, I mean, this triple product you can realize as a complex involving the functions E and F. And to prove that this is invertible, you can use the Jordan-Euler filtration and reduce the invertibility to the case of an L of lambda. And we know on an L of lambda, the action of anyway, L of lambda is very simple, and the action here can be checked to be invertible. So that's just giving some rough idea of what is happening. So this can be extended. This works. Something like that works for every Kac-Moody algebra. So you define things by generator relations, are EIs, FIs, and bigger weights spaces, and there should be some action of the bread group, partly known by Curtis Cambiaser-Licata. So there is a lot of what you can do with representations of, say, complex semi-simple algebras or Kac-Moody algebras you can do on categories. So the point of doing that has been, for example, to collect categories which have both symmetries like that, and to understand better certain categories of representations. Okay, so that's right. So now I'm going to start going towards topological applications. So in the 90s, Reshetin and 2IF realized Wheaton's proposal for 3D Chern-Simons invariants using representations of quantum groups. Puts affinity. So if you think only of link invariants, you're really thinking of you can take the quantum group QQ of G to any parameter, generic in particular. And Kren and Frenkel suggested that maybe if instead of considering actions on vector spaces, we consider someone invented a concept of action on categories. By doing that, maybe one could get could categorize those invariants and Reshetin into IF and get invariants of 4 manifolds. So that was that has been one of the motivation for not for me but for some other people at the beginning to go in these directions. And the most successful, I mean, the first successful thing in this direction is a construction by Kovanov of his homology theory. So that did not rely on higher representations. That's something he did directly, but that was still in this spirit, and that now does fit with this two representation theory framework. Right. So so one thing about Reshetin into IF invariants is that the crucial aspect is having a tensor product for representations and the braiding. And there are analogs of that in this setting where you look at categories instead of vector spaces. So I write the tensor product slightly differently because it's because of what I'll say in a minute. Which is that the forgetful functor. So a two representation is a category with some extra structure. So when you forget the structure, this extra structure, that functor is not monoidal. So that means if you take this whatever this tensor product is for two representations, it's something that you is not the same as, say, tensor product on additive categories or K-linear categories. So more concretely, if you take V and W with this higher representation structure, you can perform a tensor product. There will be an action on that, but even the under category depends on more than the V and W as categories. So if you know V and W as categories, you don't know what is the category underlying this tensor product, which is, yeah, wouldn't be the case if that functor was monoidal. And you don't need the full G action, you need only the action of the positive part. Depends only on the G plus action on V and W. So I don't know why it's like that. I mean, from the point of view of field theory, topological field theory is reduced to going down to dimension 1. I mean, this would be or 0, say 0, 1 open close. There is some reason why something like that is reasonable. Algebraically, it's not clear. So there is a complication there. Is that this tensor product, if you take V and W, say some abelian categories or some DG categories, what you construct is not going to be a true representation. The sense I define is going to be only up to homotopy, and so you need to put everything in this setting, in this infinity category or infinity category setting. So that even for SL2 makes that makes things immediately rather heavy to manipulate, and that's what has slowed down some of the use of these techniques to try to get let's say three-manifold invariants, for example, as I said, to SL2 or to other simple. Right. So one example I want to give of tensor product. So again, for SL2, so I've explained that for every say dominant weight, I said there is a simple two representation, and so the analog of the vector representation for SL2, the categorical analog is fairly trivial. You take two copies of the category of vector spaces, which correspond to the two non-zero weight spaces, and E is the identity functor, say going from one copy to the other. F is just the identity functor going the other way around. So you do at the other categories the obvious thing that you maybe think what you do on vector spaces, and the map, the X and the T are both zero in this case. So this structure here doesn't seem very interesting, but if you start taking tensor products of this by itself, and you do that say n times, you're going to realize something that contains some categorical version of the n-dimensional representation, which we know is of the n+1 dimensional representation, which we know is realized in the can be realized in the cohomology or K-theory of Grassmannians, and that's something you see algebraically. This category there is equivalent to constructible sheaves on categories of constructible sheaves on various Grassmannians. You want them smooth on orbits for GRN. So that's a very interesting feature of this tensor operation into representation theory, is that you can start with very simple categories and you can build complicated ones. So what I expect is that, I mean, this has to do with dimension 2. If you think of dimension 2, algebraic geometry dimension 2, if you think of algebraic geometry dimension 3, like Calabi or 3/4 and things like that, you won't have much more complicated the algebras or all algebras or things like that. But the idea is that all those moduli spaces that you consider when you do enumerated invariants, you would hope that there are categories of sheaves. They can be obtained in an algebraic manner from very simple algebraic objects. So algebraic geometry is very good at producing geometry, at producing complicated spaces from simple spaces. You take some algebraic varieties, just a vector space, and you start doing moduli spaces of things. You get very complicated things. So algebra doesn't have many tools like that. But that's one. This tensor product here is a tool of that kind, where you would start with something fairly simple, and you produce things. You produce complicated things. So I expect that to be to work in more complicated situations for Calabi R3. So. Yes. So So this is something that's so far difficult to prove. So the problem is you can take G, you place G by you take any G, you take simples, you take the tensor product. So what you get is something that should be equivalent. So Webster has defined. So these L of lambdas are defined using certain algebras, which can be generalized, which have been generalized by Webster to something that should correspond to a tensor product of simple representation in that sense. So the difficulty is that Webster algebras, their algebras are not differential graded algebras, and they have to do with choosing a canonical in this tensor product. And here we are doing the tensor product, and the natural basis that comes in the construction is the tensor product basis. So this, when you perform this construction, if you start with, even if you start with honest algebras, like what you're going to get here, the best you can get is a DG algebra, differential graded algebra. So the conjecture is that these differential graded algebras they are the equivalent to Webster algebras, which have to do with tensor product for the canonical basis. So unfortunately, it's not clear yet how to what is a good way to prove that there are such equivalences. It's so techniques maybe that characterize tensor product, characterize certain tensor products using techniques that you've developed could be useful there, but there's still a problem with T structure, that this comes in a different T structure. There's no obvious T structure there. The one you want is a non-obvious one having to do with switching to a canonical basis. In general, it's not. More like they are like symmetric algebras, like so there's no. So that's an issue. I mean, even this proving, even in this case, understanding these tensor products, it's not very satisfactory. I mean, the perverse sheets here, they will correspond to things there that are not obvious. Yes. Yeah. So the problem is that here, the natural basis the natural things here are perverses, and the natural thing here is not. It's the natural basis somehow for this category is not the same as the natural one. So when you want to prove the equivalence, you have these difficulties that you need to So you need basically here you need to find some of the perversity structure. How do you find it there? So but still, I mean, in a particular case you can do it, but in general that's missing. I mean. Okay, so I think that's just illustrating the tensor product. So now I'll switch to I'll leave the normal world and go in the super world where we were worried. Sacha Baberman was lost this morning. He was on the outside of the world. So we leave the event side. We go in that super world. So the point is that GL11 turns out to be simpler than SL2 or than GL2. So that's why that's one reason why I talk about that. And the second reason is that there is a theory of topological invariants, low-dimensional topology invariants associated to GL11, and it's called Heegaard-Floer theory. So Heegaard-Floer theory originally is a theory developed by Oswald and Szabo. So so it's four-dimensional invariance of four-dimensional manifolds, and it's some sort of three-dimensional, four-dimensional TQFT. Not quite. And this has been extended down to dimension 2 by Lipschitz, Oswald, and not Szabo, Thurston. So it's bordered is Lipschitz, Oswald, Thurston. I'm sorry. So that's a theory that's going to associate. So to a four-dimensional manifold, it's a number. To a three-dimensional manifold, it's a vector space. Now to a two-dimensional manifold, it's a category. So it's a category that they define originally as modules of an algebra, differential algebra, which proved is equivalent to there are categories equivalent to the Fukaya category of a symmetric power of your surface. So G is the genus of the surface. And surfaces cannot be closed. That's a boundary, and there's some pictures. There are some pictures to come. So it's a wrapped Fukaya category. You have to put some stuffs on the boundary. I'll explain that. But that's basically that's what this example is about. So there's no x. I'll explain. But there's no x, and t is because the square is 0, somehow t disappears as well. So it's a theory where the t is hidden somewhere, but there's no x. That's why the theory is easier. So the difficulties have to do with x. But I'll explain. So with Andy Mannion, we following work of Douglas, Lipschitz, and Marescu, we extended the theory down to dimension 1 to some extent. And in dimension 1, we use the positive part of this Lie algebra GL11. And so what I explained before about tensor product, which I didn't define, I explained that there is this tensor product was involved some A-infinity structures. So there's a miracle there that we were able to do a construction which was rigid. There was no, things were not defined up to homotopy. And that made things considerably easier, enabled us to develop more of the theory. And so GL11 plus the positive part of GL11 is one-dimensional. It's an odd one-dimensional Lie algebra. So its enveloping algebra is is a polynomial ring on a generator E where E square is 0, because E is odd. So if we want a categorical version of that, that's what was on that blackboard, is an action of the positive part of GL11 on a category. We understand that as a data of an Endo functor whose square is not quite 0, is homotopic to 0. And the homotopy should be part of the data. It should be understood in a suitable infinity or infinity category. So, okay, so again, a representation of GL11 plus two representation is an action up to homotopy of this monoidal category. And yes, when we have a surface with S1 in the boundary, so compact oriented with S1 in the boundary, so need also a mark point on the boundary. Whenever you see that in your boundary, you can construct on this Fukaya category or the algebras of this field of Wasserstein, you can construct such a functor E. So the action is we can make it DG, we can make a rigid action again. So actually E square is not 0, its T square is comes with an endomorphism whose differential is 1. Instead of saying it's homotopy to 0, we prescribe the homotopy and then this prescribed homotopy is like this T, and it is assumed again to square to 0 and to satisfy Bragg relations. Yeah, and so we prove that we do have some sort of extent, some sort of 1, 2 TQFT, which means that, for example, this example, if we want to look at the invariant associated to this surface, we can cut it in two here, and we just have to do a tensor product of the invariants for those tensor product viewed as true representation of GL11 plus. So it's not true that the category there and the category there do determine the category to the left. This is true only if you add to this category the extra structure of representation of GL11 plus. So you need this endo functor E acting on the category there, the one acting on the category there. With this extra data, you can do this, perform this tensor operation and do that. So at the end, you can recover those Fukaya categories by chopping in. You can chop your surface and end up with something very. You can cut further along in the middle here, and you end up with just a cylinder. Yes. Yeah. So the we can talk later. But it would take me a little bit of time to explain how things act. The way people do normally is these things have to do with a counting holomorphic disk, and you do that. In this case, you use there's these ripcord descriptions, and in terms of ripcords, that's how we describe the actions. That's using this Lipschitz-Szabo algebra. So inside your Fukaya category, you need a specific generating Lagrangian, which comes from adding to sigma an arc decomposition. So it's a long story. To get the action of E is something we write down explicitly once we have endoed the surface with extra data. So so maybe I can say algebraically what I didn't say is that if you asking that E square is homotopic to 0, not 0, is prescribing an endomorphism of E square such that the differential is 1. I'm not writing degrees or whatever there, but to prove that an object is homotopic to 0, you need to find an endomorphism with differential is 1. Okay, that's a homotopy, contracting homotopy. And then, so that's really the data an infinity action of this. So what's going on in that in this case, when you can also consider a DG category that's going to be quite isomorphic to that one, which also monoidal category, whereas you impose these extra relations that T square is 0, and you impose also the Borel relation on E cube. So E square is homotopic to 0, but it's maybe not 0. E cube similarly, and you'll have you can use T to make different envelopes of E cube, and you can have this Borel relation. So this is what we work with when we deal with the Heegaard-Floer theory, and not with. I mean, the Foucault category is an infinity category, but the work of Lifshitz, Osvar, and Thurston provides differential algebras, for which we have a true action of this of such a structure. So it's not an infinity; it's really a DG. It's really strict action. So, I mean, but I'm not telling you the geometry or the symplectic geometry, how things work. It's not very complicated, but it's yeah, it's a nice picture that you have to. The pictures have to be explained in terms of the geometry of the sinus power. These records and the holomorphic disks involved. Right. So I can say what. So what we're trying to build is somehow some sort of four-dimensional topological field theory. So that it's not that four-dimensional invariants will arise directly from such a theory. There's no things don't work quite like that, but that gives an idea of the general structure, and so it should almost descend to a point. So if it were somehow the idea, the rough idea is that for manifolds of all those dimensions, you should be able to associate something. Yeah, so here you should have a number, here a vector space, here a category, and then it gets more complicated when you go down. But what you should associate to 0 to a point should be something like the category of two representations. So two representation of GL11 plus forms there's a tensor product, so that's a monoidal category. And you look at okay, so that's the basic idea of TQFT. So if they go down to a point, and so to a circle, then that would as to S1, you would associate two representations of the double of GL11 plus. So it's a very rough. So you think of that as GL11. I mean, here I didn't put I put only the Nilpotent part, but you can add. So the crucial thing is really the positive part in a sense, and then for S1 get that. So when you do, for example, Reshitik into IF, I mean, it doesn't go down to a point. You start with S1, so in the Reshitik into IF situation, you would associate representations. Then you take a root of 1. You start there, okay. But it's not very far. It's not quite true that it goes down to a point, but that's still a good. This is not quite the double of the positive part, and there's a point going to root of unity. There are a number of issues, but that's still a good guide. But anyway, when you want to go to, if you want to mimic Reshikhin and Toyas construct, say 2-dimension 3, what plays an important role is with the quantum group. I mean, the half is in some sense enough, but then you need to work with the full quantum group to get your invariants. So here I want to explain what is the two representation of the full GL11. So GL11 has a 2-dimensional Cartan subalgebras, so corresponding weights lambda 1, lambda 2. So now when you look at representations of a super Lie algebra, you should act on super vector spaces. So your vector space splits as a direct sum of its even and its odd part. And when you look at categorical analog of data, turns out that you should have not just a parity, but you should have an additional Z. Your category should split according to integers. So I there is an integer, which I should probably have. So I is in Z. And I modulo 2 is going to be your parity. So if you were to take, say, V for the V's abelian categories, or maybe try DG categories, you pass to K0. Then you would take the sum for all of VI's for I odd. That would be the odd part, VI for I even, the even part of your super vector space. So we start, so GL11, the action of E and F is going to move between weight spaces. And I managed to get the parity wrong. Okay, I'm sorry, I cannot fix that. So the I is an odd operator, so it cannot respect, it has to change the parity back to E equals I. And there are, we always have some sort of unitary, again, situation where E and F are adjoint. And there's also an adjunction the other way around, but, and again, there, okay, I realized I missed the shift. There's a shift that's that appears here. There's a shift by 2i. So there's a shift there. There's an adjunction F restricted to something. So these homological shifts there, in addition, there should be also degree shifts. Things can be graded, and that's how you find not just the Lie algebra, but the quantum group when you go to K0. But I ignored this. I didn't want to add that. So here I should put a shift. So the E and F are joined in one direction, and in the other direction there's a shift. So it's very much like in you find in situations where you take a smooth and proper map where between the lower star and the upper star there are left and right adjunctions. There's a shift. So you take these functors, you assume that E is homotopic to 0. E square is homotopic to 0, which means something like that. It's extra data. And then you, instead of the type of isomorphism I asked for SL2 or for Kac-Moody, here it's something you cannot state in an abelian category setting or an additive category. It has to be DG or something like that. So there's a certain distinguished triangle that involves EF, FE, and 2 copies of the identity. So the defining relation so relation between EF and FE in GL11, instead of EF minus FE, you get EF plus FE, because E and F are odd elements. And here you see that you have EF shifted by 1, whereas you have FE. So when you pass to K0, this is telling you something about EF plus FE equals, well, you have a copy of the identity and two copies of the identity. And when you put grading, there will be a power of. So the maps there are all adjunction maps except this map from EF to FE, which again comes from this map. So there's something a little bit more tricky here, is that this map T is not closed. The differential is 1. So it is going to induce a map between EF and FE that itself has a non-zero differential. So there is no map from EF to FE that is closed, but you can construct a map from EF to the cone of the identity to FE. That is this, from EF to FE, you use this map T. And from EF to the identity, you use the co-unit of adjunction. And the fact that differential T equals 1, you can check that means that this map from EF to the cone is now closed. Its differential is 0. So there is, you can understand this map I explained for SL2 that this has to do with the map from EF to FE, and having a map satisfying this property is the same as having a map from EF to the cone of that. So, okay, and so we ask for this triangle to be distinguished, and again, this can be stated in a different way by saying there's a certain monoidal category, and this is let's say, an infinity action of that monoidal category. Right, so this is actually simpler than SL2, even though it's always a bit derived. So this is a non-derived example that definitely get derived. So you take for E, for V, there are two weight spaces. So one is just modules over some field K, and the other weight space, it's not like for SL2 where you can take vector spaces on both weight spaces for the vector representation. Here on one of the two weight spaces, you need to take this algebra. And the functors are as explained. So this is the categorical version of the vector representation for GL11. And that's an example. So now you can, here you can use the tensor product for two representation and you have a braiding and twist. You get some sort of ribbon category. So it's a higher version, and you want to state it precisely to prove that you have some sort of monoidal to category that's or ribbon to category that's a lot of structure. So one thing that you can check is that things work up to isomorphism. So it's some sort of ribbon category and rich triangulated categories, and that's good enough to get you link invariants or tangle invariants. It's the same way as the usual merged it into IF way. And again, I mean, if you were to start with say SL2 or SLN, well, let's say if you do SL2, if you take the vector, if you take a link and you color its components with the vector representation, you're going to recover the Jones polynomial. So here you expect, if you do use the vector representation, you expect to get the categorification of the Alexander polynomial. And this is already something that has a categorification. That's something you obtain from Heegaard-Floer theory. It's called the note Heegaard-Floer. And that's the construction of Barsabo and of Rasmussen. And so the expectation is that here, if you use this notion of two representation, you have this category of tensor product, you have a braiding. If you apply, if you make tangle or link invariants using V, you're defining representation, so its dual is going to be involved, everything is oriented there. Then the link invariant you get should be, it's probably going to be so that can be defined, but the expectation is that it is this not invariant coming from, or link invariant coming from Heegaard-Floer theory. So the surface case of Heegaard-Floer theory, we know it's something we can get from higher representation of GL11, at least, or even the positive part is enough. And so for nodes and leaks, there's some evidence that yeah, things work. So the next step will be to get invariants of 3 manifolds, recover them like that, and hopefully, I mean, doing GL11 also should be a good indication for what to do for the non-super case, so the case of SA2 or the complex loops. And then dimension 4 is where the story gets really interesting for Heegaard-Floer, where this hat theory, this Heegaard-Floer theory I was talking about, is trivial for manifolds. So there are deformations of the theory that you need to use, plus or minus versions, and then you need to do something a bit more complicated for manifold before you apply them, find these theories. But so this hopefully has this whole theory for GL11 should deform. We expect it to deform, but we don't know yet how. In 2 ways, to minus and plus series, and that would be the step to take for manifold. Okay, let's stop here. Sorry. It's the way it's done is not like that at all. It's by counting holomorphic disks. So it's defined. I mean, I don't know. It's just the same. They construct not invariants using. Yes. No, exactly. Yeah, exactly. Yeah. I hope. Yeah, yeah. Which is the expectation? This decategorifies into the Alexander polynomial. Yeah. 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 Yes. But, yeah. Thank you.
Yes.
So at the very first beginning, when you were defining two representations, you mentioned the coherency in some endomorphisms on E3, right? But why is it only on E3 and not higher objects? Is it some kind of McLean coherency theorem or just purification?
It's similar to what you do in a braided monoidal category, where you ask for a braiding. So you have this braid relation there, which is. I mean, you have this coherence result. I mean, from this relation, you will, if you think of commutativity, someone substitute for commutativity in a monoidal category, the weakest you can do is a braided monoidal category, and that has to do with diagrams like that.
So you mean like some coherency theorem implies that this will give us all the other commutations we need?
Here it's simpler. We don't have this issue. It's really what's underlying that are Heegaard algebras, and we are saying there is some like Heegaard algebra symmetry groups or generalizations, and they are defined by generator relations by using braid relations. So I mean, I don't know why there are no relations for e to the fourth anywhere. I don't know that. I don't know. But yeah, I don't know. The answer to your question is I don't know why this is enough. No,
First of all, is it sufficient we just to do something with Bardisms, or you need a infinity structure to even to prove t squared equals 0? Is it some kind of picture with Bardisms right now, or it is the whole machinery?
So t squared equals 0 in it's a classical in the Heegaard-Floer theory. It's a classical relation. This picture with 0 in that theory. You do a crossing twice, but that comes.
But do we need calculations up to homotopy?
No, this is
no.
I mean, all these things in Heegaard-Floer, all the hard things have been done by people Heegaard-Floer
So
theory
that's
before.
one thing
Yeah,
actually was maybe complicated.
Yes. There's no everything on the Heegaard-Floer, or everything on that side of second part of the talk. There is basically no infinity, nothing up to homotopy.
Questions? No, let's thank our speaker again.